Hello guys, my name is Balkrishna and welcome to Code with BK. So in this video, we learned a Java program to calculate the value of natural log given a value x using series. So before we begin, it is a request to please subscribe to my channel, because out of 100 views, only 1 or 2 is subscribed, and your subscription is very important. So please do subscribe to my channel. So let's begin. So ln x in series can be written as 2 into sum of, starting from 1 going till infinite, we have 1 by 2I minus 1 into x minus 1 upon x plus 1 to the power 2I minus 1. Okay, x is greater than 0. This series is valid for x is greater than 0 and n greater than 0. Okay, you have to estimate ln x for given value of x greater than 0 using the first n terms. Alright, this is the problem. Okay, so when you are estimating using the first n terms, I goes from 1 to n. So we solve this using two approaches. The first one is going to be brute force. Okay, we don't make any optimizations whatsoever. The second one is going to be a little more optimization, so it will be the faster version. Okay, optimized version. Okay, alright. So let's do the first case, brute force case. In brute force case, it is very straightforward. Okay, you start with I equal to 1 till n. You calculate this term, okay, and you add it to a recurring sum. Okay, so I'm going to say double because the return type of this function is going to be a double value. ln x 1. Okay, this is the first approach to find the value of ln x. Okay, it takes a double value of x, of which you need to find the natural log, and for the first n terms of this series, using the first n terms of this series. Okay, we start with the sum equal to 0, double sum equal to 0, and we have to sum all these terms starting from 1 to n. So let me expand this. So this comes out to be ln x is equal to, for I equal to 1, this is equal to 2 into x minus 1 upon x plus 1 to the power of 2 into 1 minus 1, which is 1. Okay, plus this for I equal to 1. Next one is going to be 2 into 2 minus 1, this is going to be 3. 1 by 3 into x minus 1 upon x plus 1 to the power 3 plus 1 by 5. Okay, for I equal to 3. So this is for I equal to 1, I equal to 2. I equal to 3, this is going to be x minus 1 upon x plus 1 to the power 5 and x minus 1 upon x plus 1. 1 by 7 for I equal to 4 to the power 7 and so on. Okay, for I equal to n. Okay, for the first n terms, we find the sum of this series. Okay, and we multiply it by 2. Okay, so you see x minus 1 upon x plus 1 is common, so I'll take it in a separate variable, double y x minus 1 upon x plus 1. Alright, okay, I started I equal to 1 and go to less than equal to n. For int I equal to 1, I less than equal to n, I plus plus. So my ith term is 1 by 2i minus 1 into x minus 1 x plus 1 by 2i minus 1. So my double t term is going to be 1 by 2 into I minus 1. Okay, into, okay, this part is 1 by 2i minus 1 for this I. Okay, into x minus 1 upon x plus 1 to the power 2i minus 1 into math dot pow to calculate a to power b. X minus 1 x plus 1 is taken into y to power 2i minus 1, 2i minus 1. Okay, alright, and this 1 has to be 1.0, not 1. If you take it as 1, okay, if you take it as 1 and you calculate 2i minus 1, for I equal to 1, this is going to be 1 by 1. Okay, this is going to give you 1 for the first term, which is okay. For I equal to 2, this is going to be 1 by 2 into 2 minus 1, which is going to be 1 by 3. Okay, 1 by 3 here is integer division, because this is integer, this will give you 0. Similarly, I equal to 3 will give you 1 by 5 equal to 0. Okay, if you don't make it 1.0, alright, because this is integer division, integer by integer, and since numerator is always 1, okay, and your denominator is always greater than 1, that's why we said 1 to 1.0 and not. Okay, so that it is a double divided by an int. Okay, If you do 1.0 by 3, it gives you the actual value, which is 0.3333. And if you do 1.0 by 5, which is it gives you 0.2. Okay? Alright, that's how you make it 1.0. The first thing you need to keep in mind. Alright, so we keep it 1.0 and not 1 because apart from the first term, all the others will be multiplied by 0. Okay, we don't want that. Alright, you calculated the term, you have to add it to the sum. You say sum plus equal to t. Okay, and you return the sum. Okay, so this is the code to estimate the value of natural log x for the first n terms. Okay, and you have to return 2 into sum. Alright, okay, and this is a brute force approach, and I'm going to run this on the system. Okay, and I'm going to compare it with math.log, which is the inbuilt function, to find the value of natural log. Okay, I'll pass x, the same x, to this and this, x greater than 0, and then I'll compare. Okay, I'll show that in the code. Okay, alright, moving on to the second approach now, which is the faster version. Okay, we make some optimizations in this, and I'll make optimizations in this very code. Okay, alright, so I'll say my first term is x minus 1 upon x plus 1, which is basically y. Okay, my second term is 1 by 3 into x minus 1 upon x plus 1 whole cube. Okay, which is equal to 1 by 3 x minus 1 upon x plus 1 whole square into x minus 1 upon x plus 1. So x minus 1 x plus 1 is basically a first term. Okay, so you can say 1 by 3 x minus 1 x plus 1 whole square into your first term. Alright, okay, writing the third term, I have third term. Okay, I'll remove this. I have third term as 1 by 5 x minus 1 upon x plus 1 whole 5. Okay, so this is basically 1 by 5 x minus 1 upon x plus 1 whole square into x minus 1 upon x plus 1 whole cube. Okay, I mean, I really like doing this because I'm doing this after a long time. I'm MSc Physics after all. Okay, not getting my nerd mode on. Okay, so x minus 1 x plus 1 whole cube, okay, is basically this term. I need to divide it by 3. So I'll multiply and divide by 3. Okay, so this 3 I bring here, so it becomes 3 by 5 into x minus 1 upon x plus 1 whole square into x minus 1 upon x plus 1 whole cube into 1 by 3. Okay, now this is my second term. Okay, 1 by 3 x minus 1 x plus 1 whole cube. So this is 3 by 5 x minus 1 x plus 1 whole square into a second term. Okay, taking the fourth term is equal to 1 by 7 into x minus 1 upon x plus 1 to the power 7. Okay, alright, this is equal to 1 by 7. I will extract this part x minus 1 x plus 1 plus 5. So I'll say x minus 1 x plus 1 whole square into x minus 1 x plus 1 to the power 5. Okay, multiplying and dividing by 5 into 5 and divided by 5. Bringing this 5 here, this 5 here. Okay, 5 by 7 x minus 1 x plus 1 whole square x minus 1 x plus 1 whole 5 into 1 by 5. Now this is your third term. Okay, so this becomes 5 by 7 x minus 1 x plus 1 whole square into third term. Alright, so let me generalize this. This is for I equal to 1, this is for I equal to 2, I equal to 3 and I equal to 4. So for I equal to 1 I have this, so I can label this as T1, T2. Okay, so this is my T2. Okay, this is my first one, this is T1, this is T3 and this is T4, fourth term. So I am able to write the second, third and fourth term, okay, in terms of the previous term. So apart from the first term, from second term onwards, basically you can write the term in terms of the previous term. Okay, so let me generalize this, let me remove this. So let me write this second term in terms of the first one. So this is basically for I equal to 2, I have 1 by 3 x minus 1 by 3 y square into first term, 1 by 3 into y square into first one, which is T1. Okay, so I do I minus minus first, right? I minus minus, so implies I becomes 1. and then I'll do 2i minus 1 upon 2i plus 1 into y square of t1. Okay, so 2i minus 1 for I equal to 1 is going to give you 1. 2i plus 1 for I equal to 1 is going to give you 3. So 1 by 3 into y square into t1, which will give you the second term. Similarly, for third term, I have I equal to 3. I do I minus minus, I becomes 2. And same general formula, 2i minus 1 upon 2i plus 1. Okay, y square into previous term. Okay, so 2i minus 1 is going to give you 3 for I equal to 2. Okay, we are doing I minus minus first. Okay, and then you get 2i plus 1 as 5. Okay, so 3 by 5 into y square into t2, 3 by 5 into y square into t2. Okay, second term. Similarly, we take I equal to 4 here. Okay, we do I minus minus first, I becomes 3. Same formula, 2i minus 1 upon 2i plus 1 into y square into t3. Okay, previous term. Okay, 2i minus 1 will give you 5, 2i plus 1 will give you 7. 5 by 7 into y square, 5 by 7 into y square, this is y. Okay, into t3, which is the previous term. Alright, so this is the optimization I do in my code. Alright, okay, so I'm going to add the first term as it is. I'm going to say sum plus equal to y. Alright, my first term is added. This term is added. I need to start adding from I equal to 2. Okay, so I'll start with I equal to 2. Okay, I'll go to less than equal to n, I'll do I plus plus. Okay, and I also need to find the previous term. Okay, before calculating each term, so I'll say double last term equal to y. Okay, because when I have to calculate term for I equal to 2, last term is going to be x minus 1 upon x plus 1. Okay, for this case, for I equal to 2, my previous term is this y. So I have taken last term in a separate variable. Okay, alright. So my t is going to be 2i minus 1 upon 2i plus 1 y square into previous term. So instead of calculating t like this, t is equals to 2i minus 1 divided by 2i plus 1 into, okay, y square into y into y, okay, into the previous term into last term. Okay, alright, this is your next term, and every time you calculate the next term, you have to set last term to the this term calculated. Alright, okay, and you can see from second term onwards, I have to reduce I by 1 to find the general term. Okay, so for second term onwards, I have to do I minus minus. Okay, so for second, for I equal to 2, we need I equal to 1, for I equal to 3, we need I equal to 2, and so on. Okay, but if I do this, I will get decremented and incremented again. So it will always stay 2. Okay, 2 will become 1, it will go back to becoming 2, it will become 1 and again go back to becoming 2. This will be infinite loop. So I am not going to do this. I am going to shift all the range for I one step left. Okay, so I, rather than going from 2 to less than equal to n, I go from 1 to less than n. Alright, so if n equal to 5, okay, I takes values 1 to less than equal to n, 2 to less than equal to n in the original case that we had. So 2, 3, 4, 5. Okay, so I takes for n equal to 5, second, third, fourth, and then the fifth term. Okay, but for each I have to do I minus 1. So I minus 1, when I do to each I, it becomes 1, 2, 3, 4, which effectively becomes 1 to less than n. So that's why I did 1 to less than n. Alright, okay, so that you can find the general terms. One more thing you need to note here is this division is currently giving you 0 because this is integer by integer. So if I have I equal to 1, right? 2i minus 1 gives me 1, 2i plus 1 gives me 3. 1 by 3, integer division is 0. I have I equal to 2, 2i minus 1 is 3, okay, 2i plus 1 is 5, 3 by 5 integer division gives me 0. So this will always give 0, so t will always be 0, okay. So to change that, I have to have either numerator or denominator to be a double. So I will bring this numerator here, okay, I'll say 2i minus 1, okay, and I'll bring 1.0 by this denominator. Okay, so now this is a double value, this is a double value, this is a double value, and multiplied by integer will give you a double value. Alright, okay, and this is my updated faster lnx2. Okay, and I'm going to run this on the system along with lnx1. So this is lnx2, sorry, and I'm going to compare it with math.log, which finds the natural log. This is the inbuilt function in Java. Okay, I'll compare them for the same value of x greater than 0. Okay, so this was the solution to this problem, and I hope this was helpful. And I got to do this after a very long time. So I mean, good feelings about this, very long time. Okay, all right. So before moving on to the system and running this, okay, testing this out, it is a request that if you like this video, if you find this helpful, please do subscribe to my channel, and let's move on to running this on a system now. So these are the two functions that we wrote and discussed. So this is to find ln x using the brute force approach, and this is to find ln x using the optimized approach. All right. I have a compare method that I'll come to later. All right. And then in my main, I take certain values of x, and these are all greater than 0 because the series that we took is valid for greater than 0. All right. For x greater than 0. So for each x in this array, I calculate ln x first using brute force, calling ln x1 passing x and n. Similarly, calling ln x2 passing x and n, that calculates ln x using optimized approach. All right. And then I compare these two values against the math.log function, which is inbuilt in Java. This calculates natural log. So if I take my pointer here, okay, returns the natural logarithm, okay, base e. That is what we are calculating. All right. So let me run this. So ln 0.25, the first value of x. Let me make this a little to the right. Okay. For the first value of x, you have minus 1.38, and this is the actual value. All right. So this is correct. All right. Very close. Only this is the difference. Okay. Similarly, for 0.11, I have this, and I have this. Okay. Again, this value is almost the same. Okay. These two values, brute force and optimized approach, are the same. Similarly, this for 1.93, 1.93 against this actual value. Okay. Then 8.34, 8.34, I have this, and the actual value is this. Okay. Very minute difference. Similarly, for 101.12. All right. Okay. And similarly for 34.5. All right. Okay. So the purpose of telling you this and this approach is that this second approach is faster. So how do I know if my second approach is faster? Because right now all I can see that they both produce the same values. Okay, very close to the actual math.log value. All right. To check their running times, I have written a function compare. This takes the double access array that I have here in the main. So I called compare passing access. All right. So in this function, for each value of x, I have n terms. So n terms are 100, then 200, then 300, 400 till 1000. Okay. So for each value of x and for each value of n, for each value of x and for each value of n, I calculate ln x1, that is I calculate ln x using brute force, which I am doing here. All right. And I also need to time how long it takes to calculate ln x1 using x and n. So I start the timer before I call this function, and I stop the timer after this function returns. So the time taken by ln x1 to calculate ln x using the first n terms is this, stop minus start. Similarly, I calculate ln x2 using x and n, first n terms for this value x, and again I start the timer before calling the function and stop the timer after the function returns, and then the time taken by this function is stop minus start, which I am storing in this variable. Okay. So for each x and each n, I calculate ln x brute force. Okay. The time that this function takes is stored in time brute force. Then I calculate ln x optimized using this function, which I print here, and the time that this function takes is time optimized, which I am printing here. Okay. I am using system.out.printf to print this in neat columns. Okay. I've already posted a video on system.out.printf. I'll add the link to that video in the description. All right. So let me run this. So this was our first output. Okay, this is our output when we call the compare function. So for each value of x, the number of terms I'm using are 100, 200 till 1000. All right. So ln x1 using brute force is this. Ln x2 using optimized approach is this. So the thing to note here is the time taken by the functions. So the brute force function takes 11581 nanoseconds, but the optimized version takes much less. All right. And you can see the optimized version takes always the lesser time. Okay, for the same x and for the same n. All right. Similarly, for this other value of x, n terms from 100 to 1000, again the optimized version takes lesser time. Okay. And similarly for this x, similarly for this x, similarly for this x, and similarly for this x. Okay.
if I make this 1000, okay, till 10,000, and every time I increase 1000, so instead from 100 to 1000, this goes from 1000 to 10,000. So let me run this, okay, and now you can see the significant difference in time. Okay, so this was the solution to this problem, and I hope this was helpful. So if you like this video, if you found this helpful, please do subscribe to my channel, please like my video, and please share my channel. And if there is something that you dislike about this video, don't just press the dislike button, because if you don't let me know in the comments what you don't like about this video, I cannot improve upon it. All right, and you can also post in the comments if there is a question you want me to solve, or if there is a concept you want me to discuss. Thank you.